I've written a console program to do the performance measurements, and I'm using a base class called performance test right here to run the performance, the different performance tests. I have three methods here: measure test A, measure test B, and measure test C. So these are virtual methods, and in any derived class I will put the test code in here. And the format is always that the first one, test A, is the baseline test. So this would be unmodified slow code, and then we have two methods B and C available to try out different kinds of optimizations. And then for the actual performance test down here, the performance test is fairly simple. Basically what I do is I go through these test A, test B, and test C methods, and I repeat them a number of times. So you can see there's a constant here, default repetitions, with a value of 10. I basically repeat the tests 10 times to average out the effects of the garbage collector, because an ill-timed collection of the garbage collector can really slow down one of the tests. So if we just run it 10 times, then we average out that effect. To measure performance, you're supposed to use the stopwatch class in C#. So when you're doing benchmarking, please don't use date time. Always use stopwatch, because stopwatch is a specialized class for measuring time spans extremely accurately. So you can see I always start by restarting a stopwatch, doing the test, stopping the stopwatch, and then I have the elapsed milliseconds right here, and I'm adding that to a variable. And then in the end, you can see right here, I'm returning that total value divided by the number of repetitions. So we're doing 10 repetitions, so we have the total elapsed time for every method, and then divided by the number of repetitions gives you the average execution time. Okay, moving on to arrays. Let me show you the array test. I have a very simple piece of code. I declare a three-dimensional array. So I have an array with 3 dimensions. Then I have 3 nested for loops to fill the array. And in the innermost loop, all I do is increment every array element by 1. So super simple. So that's test A. Test B uses a one-dimensional array, and it's flattened. So I have a one-dimensional array that has the same size as the three-dimensional array, and I use this simple formula to calculate the index into this one-dimensional array using the I, j, and k variables, and then I do the same operation. Finally, I have a one-dimensional array. I use I, j, and k, but now you can see I simply have an index variable that starts at 0, and I increment it by 1. So instead of using this formula with the multiplication and the addition, I just have a simple variable that incrementally goes through the entire array and initializes it. So let's take a look at the performance of these arrays. So I'm running test 2, 300 iterations with a baseline. Here we go. And here's the result. The three-dimensional array is slowest, the flattened one-dimensional array is faster, and the array with incremental access is the fastest. Now, you might be wondering right now, what's going on? Why is a three-dimensional array slower than a one-dimensional array with the exact same logic? I mean, if you think about it, this expression, the .NET framework needs to do this exact same calculation to find the memory location of this threefold array index. So either I'm doing the formula or the framework is doing the formula, but it's the same mathematical expression. So why do we see this difference? So to explain that, I'm going to have to show you the intermediate language code of this compiled program, which I have right here. So let's go to the array test. Arrays test, plural. So here it is. Here's the array test class. This is the constructor. Let me just scroll down. And this is measure test A. So the code to access the array element is right here. So you can see this instruction loads a location, loads a local variable of the stack. So 0, 1, and 2 are the I, j, and k variables. And then this call does the array indexing. And you can see it's actually a method call. It's an instance call to the array class, and within that class it calls a method called address, which expects 3 parameters. So behind the scenes, the .NET framework implements a 3-dimensional array as a class, and any interaction with that class goes through methods. But now let's look at the 1-dimensional array. So that's right here. And the operations are here. So this is the code to index into a 1-dimensional array, and the thing I want you to notice is this instruction here called load element address. Load element address indexes into a 1-dimensional array and returns the address of that element. So to work with 1-dimensional arrays, the .NET framework, the .NET runtime, has a specialized CIL instruction. So load element is optimized, is specialized to work with 1-dimensional arrays. So there's no method call. I don't have to go into a method and run some .NET framework code to get at the array element. It can all be done with CIL instructions. The only method calls in this block of code are these two, and they are only needed because my array dimensions are stored in this property. If I had used an array with a constant dimension, a constant size, this call wouldn't be there, and it would simply be a load instruction to load a constant value. And then this entire block of code wouldn't have any method calls whatsoever. So the takeaway I want you to remember is that 1-dimensional arrays in .NET, the intermediate language has optimized instructions for dealing with them. So a code that uses a 1-dimensional array will always be faster than code that uses 2, 3, 4, 5, or 6-dimensional arrays because of the difference in implementation in the .NET runtime.